Okay. Before I start this part of the lecture, I wanted to tell you something very important for the third exam, and that is your ability to work with your calculator, okay? Most of it is complex analysis, complex calculation, and that goes a long way. So if you don't know how to do complex analysis or complex calculation with your calculator, it's going to be a real problem, okay? Much more than the first two exams. So start learning to work with that. Do whatever you can at home when doing web work with your calculator, not just some online tool or MathCAD, so that you learn to work, to become handy with it. Now, complex numbers are based on the definition of a square root of -1. I mean, usually in real numbers, we don't have that defined. A square root of any negative number is undefined. But in complex analysis, we define that as I or J. I is basically or mostly for mathematics and physics, and J is usually used in electrical engineering. For example, if you have a number -4, I can write that as 4 times -1, and then I can write that as square root of 4 times the square root of -1, and then I can write it as 2j. Okay? That's how you define square root of negative numbers. Instead of writing 2j, I may write it as j2. Okay? So this is not uncommon to write it as j first and then the coefficient. Okay? Now, a very important concept in complex number is how we represent them. For example, for real numbers, how do you represent real numbers? The 1D line, you can show any number on the line. For example, if you set 1 point on the 1D line as 0, then you can show any number somewhere on across that line. But for complex numbers, 1D is not enough. The reason for that is that, let's talk about the first representation and then we will see why. So complex numbers are made of two components, okay? The real part and the imaginary. Every complex number is defined as real part x plus j times imaginary part, okay? So in order to represent any complex number, we need at least two separate, unrelated numbers, the real part and the imaginary part. One thing that students usually make mistakes on is that when I ask them what's the imaginary part of z, they answer by jy. That is not the imaginary part. The imaginary part is y, okay? Only y. So remember, it might be actually counterintuitive, but both real and imaginary part are real numbers. But the only difference is that the imaginary part is multiplied by a j, okay? And the real part is not multiplied by anything, okay? For example, just to make this a little more clear, z1, some random example, 3 plus j2 is a complex number. Why? Because it has a real part and it has an imaginary part. Can you tell me what is the real part? 3. What is the imaginary part? 2. Why 1? Yes. And the coefficient of j, as I mentioned, sometimes I write it after j, okay? You thought it's j squared? Yeah. How about z2? What is the real part? 0. What is the imaginary part? 5. z3. What is the real part? What is the imaginary part? So can you verify if this statement is true? Any real number is actually a complex number. Is a subset of complex numbers, real numbers, right? The only thing is that their imaginary part is 0, okay? So, since I need two numbers to represent any complex numbers, do you agree that I need a 2D plane? So this is a 2D complex plane that I can use to represent complex numbers. Now, the horizontal line is called the real axis, and the vertical line is called the imaginary axis. For example, for a number x plus jy or x plus iy, what's the real part? X. So I move from origin along the real axis by x value. That will give you the distance, the horizontal distance. And then I move along the vertical axis, which is called the imaginary axis, by y. And that will give you the distance, the vertical distance. Now, the intercept of these 2 points is your specific complex number, x plus jy. Did that make sense to everyone? Any point that you point out on the 2D complex plane is going to represent a complex number. The horizontal distance is the real value, and the vertical distance is the imaginary value, okay? Any other problem? No? Okay. Now, I'm going to ask you a question. So imagine that, for example, I'm in a jungle or a desert, and the real axis and imaginary axis are drawn for me on the ground, so I can see them. And I'm standing on the origin point. I'm standing right here. Okay? I wish I were this thin, but I'm standing right at the origin. How can you direct me to move from origin to point where z is located? First, tell me based on this representation. Based on this representation, remember, I'm standing at the origin, and I can see the real axis and imaginary axis on the ground drawn for me. So how can you address the z point to me? Or how can you direct me to move from origin to z?
Forward x, left 1.
Sorry?
Forward x, left 1.
Yeah, you can tell me to move along the real axis by x, and then move along the imaginary axis by y, exactly 90 degrees. And I will reach the point. Do you agree with that? Perfectly unique. Can I end up in some other point if I'm not stupid? No. Okay, so this is perfectly unique. What is the other way of directing me to that point? An angle and a distance, or a length, right? Pardon me? No, nothing to do with the slope, no. Slope has a meaning when you have a function dependent variable and an independent variable. These are both independent variables. So if you want to draw a function, you need a third axis, okay? That's why complex numbers are actually complicated in terms of integrating, because you need one extra dimension. Okay, so as you mentioned, the other way of representing this point is using the distance, or as we call it, the magnitude and the phase or angle. Theta z and the magnitude of z. Why do I call it magnitude? Because it's a distance. Can it be negative? No. A positive real number, okay? A positive real number. And theta is just the angle. So this is another way of uniquely determining one point on the 2D plane. This is how we show that. Any complex number z can be uniquely represented by some magnitude and some angle. Just note that that symbol is just the angle symbol. It's not an operation, at least not right now, because we don't know what it does. But we know that it is the sign of an angle, okay? And your calculator most definitely has this one. Any problem so far? Anything confusing? Okay. So this is called polar representation. The previous one was called rectangular or Cartesian representation. Okay. Now, is there any way that if I have the magnitude of z and theta z, I can transform this to x and y? Can I do that? How? Yeah. So if I multiply the magnitude of z by cosine of theta z, it will give me x. And if I multiply it by sine of theta z, it will give me y. So I can easily transform from polar to rectangular. How about if I want to go from rectangular to polar? I have x and y. How can I change it to the magnitude of z and theta z? Yeah. So a square root of x squared plus y squared will give you the magnitude of z, and the inverse tangent or arctangent of theta should be y over x. Sorry, theta is arctangent or inverse tangent of y over z. Okay, second one is good. Or I can say that the tangent of y over x is equal to, the tangent of theta is equal to y over z, which means theta is equal to inverse tangent of y over z. Okay, this is great. I'm tired. And this is exactly what we talked about, how to transfer from rectangular to polar and from polar to rectangular. For example, look at the first example. If I have a complex number, z1 equals 3 plus j4, how can I change it to polar? First, I need the magnitude. 3 squared plus 4 squared, which is 5. Then I need theta z1, which is the inverse tangent of 4 over 3. I think I remember it was 53 degrees, roughly. Is it? Okay. So what is your number? 5 angle 53 degrees. So whether you write 3 plus j4 or 5 angle 53 degrees, these are indistinguishable. They are the same point. How can I go from polar to rectangular? X, which is actually the real part of z1, is equal to what? 5 cosine 30 degrees, which is 5 this, and y, which is the imaginary part of z1, let me write them x1 and y1, is equal to 5 sine of 30 degree, which is, so your number z1 is equal to x1 plus j y1, and it's equal to 5 root 3 over 2 plus j 5 over 2. Okay? Do you need to know how to do it? Probably not. But it's very important to be able to transform whatever answer your calculator is giving you to the other representation. Very, very important, because for different problems, it's easier to work with one of these representations. And it's very important to be able to change to that specific representation, okay, whenever you want. Now, one of the brightest minds of mathematics, Euler, okay? The first very important thing, not for your exam, in order not to walk on my nerves, is that don't call it Euler. It's Euler, okay? And this is one of the, probably the most important or famous formula in complex analysis, Euler's formula. E to the power of j theta is equal to cosine theta plus j sine theta. Remember, I'm going to write this in another way because apparently students don't like the variable theta. They think of it as something confusing. So I'm going to write it like what? Any suggestion? Okay. I think you remember that. So what is it equal to? Whatever plus j sine whatever. Very important. Now, I don't need you to learn this proof, but I'm going to follow along the lines and just learn what it's saying. So you agree that any complex number can be written in this form, x plus jy. This is something that we have from rectangular representation, right? And you know that instead of x, I can write the magnitude of z cosine theta z, right? And instead of y, I can write magnitude of z sine of theta z. And the j is j. Now, I can factor out the magnitude of z here. And inside the parentheses, I will get this. Now, based on Euler's formula, instead of inside the parentheses, I can write e to the power of j theta z, right? So what did it give us? It gave us another representation for complex numbers. Instead of writing x plus jy, I can write magnitude of z exponential of j angle, okay? This is called exponential representation. And that's not actually different from polar representation. The way we write them is different, but they are technically the same thing. And I'm going to explain that to you why. So, for the polar representation, do you remember the symbol angle, the angle symbol? Okay. So, do you know what it does in terms of mathematics? Is it an operation or something? The angle. I mean, I don't. So it's not an operation. It's just the way that we denote something. Okay? So it's not an operation. What it actually does is that the angle symbol calculates the exponential of j multiplied by the angle. Okay? So that's why I'm telling you that these two representations are exactly the same thing. The only thing is that writing it in the green form is much easier, and putting it in your calculator is much easier. Your calculator has the ability of recognizing that angle sign, angle symbol, and that's why it makes it much easier to put in numbers in polar form, okay? Did that make sense to everyone? Okay, let's write this number, -5 plus J3 in polar form. What should I do? Yes, so first I will calculate the magnitude of Z1, which is -5 squared plus 3 squared, and it's equal to square root of 34, which is 5.83. That's what I have. What's next? The angle of Z1, or the phase of Z1, theta Z1, is equal to, yes, excuse me. So inverse tangent of 3 over -5. Give it to a calculator and give me the answer. -30.996 degrees. Okay? Yes?
Is this important to, like we have -30.96, is it important to put it,
Wait.
okay.
Yeah. Yes. But wait. Okay, so how can I write this in polar form? I can write Z1 is equal to 5.83 with the angle -30.96 degrees. Or I can write it in exponential form, which is 5.83 exponential of J -J 30.96 degrees. Okay? Now, can we show where Z1 is located on the 2D map? I should go 1, 2, 3, 4, 5 units to the left and 3 units up. So that is Z1. Look at your answers. Where is that located? It's 5.83, but what is the angle? That is -30.96 degrees. And if that length is equal to 5.83, which I guess it is, then that is the answer that you found. Is it Z1? They should be the same point when I say exactly the same representation. Is this the point that you were supposed to write the polar form for? No, it's not. So what should I call this? Not Z1. What went wrong? Why? The calculator gives you a default answer based on the 4th quadrant. But your answer is not in the 4th quadrant, is in the 2nd quadrant. In fact, if I want to write it correctly, what is this angle? It's -30.96 degrees plus 180, okay? So which is 149.04 degrees. Okay, how can we know that our answer is correct or no? Look at x and y of the number that is given to you, and you can just imagine which quadrant it is located. So you go left by 5 and up by 3. Which quadrant is it? The second one, 2. But your answer is in the fourth quadrant, so it shouldn't be the case. Okay? This is something to be careful with, especially when you are calculating inverse tangent. That's usually when this happens. Any problem? This is just so you know, just to refresh your memory for the quadrants. One more thing that I want you to be careful when working with your calculator is that it has 2 modes, degrees and radians, and this is sometimes the source of the mistake, okay? So remember this. Okay. Now, this is a very important concept in complex analysis, mathematics, and also physics. You don't need to be able to work with it or whatever, but I want you to understand what is it about and just get the idea behind it. So we have a concept called complex conjugate, or sometimes in short we just call it conjugate, okay? When in the context of complex analysis. What does it do? Geometrically, whatever point that you have on the 2D plane, if you mirror it about the horizontal axis, you are actually conjugating it, okay? For example, look at Z. This is Z. It's some x plus jy. Now, if you look at the mirrored version, do you agree that x is x? Both of them have the same horizontal distance. How about the vertical distance? If the original one is y, the conjugated one is negative y, right? So this is called z conjugate, shown by asterisk above z. Okay? This is called z conjugate. What if the number is given to you in polar form? So look at z. It has some distance, some magnitude, and some angle. Does the distance or magnitude change when conjugating? No. The red line is the same, okay? How about the angle? If it was 30 degrees, it becomes negative 30 degrees. So how do you conjugate a number in polar form? You don't touch the magnitude. You only add or multiply a negative sign to the angle. How do you conjugate a number which is given to in rectangular form? You keep the real part as is. The imaginary part should receive a negative sign, okay? This addition and subtraction, you're never going to use this in this course because your calculator does this for you. But I just want you to know that, for example, if I'm adding two complex numbers, okay, the real part should be added together, the imaginary part should be added together. So you need to do two addition, actually. The same for subtraction. For multiplication, it's not that easy, especially in rectangular form. So, for example, I have two rectangular form numbers, z1 and z2. How do you multiply them? You're familiar with the product of two parentheses, a plus b and c plus d. Whatever you do for that, you do the same for this, simplify the answer, and you get something that you never gonna memorize, and it's not very intuitive. But let's see what happens when the two numbers that are given to you are in polar form. Okay? So if two numbers are in polar form, you multiply the magnitudes and you add the angles. Have you seen something similar before? By before, I mean throughout your life. In any math course, have you seen something similar? Sorry? No. Yes. How do you calculate this? How do you calculate this? You multiply the 5 and 10, the coefficients, which is 50. Then, and why do you treat it like that? Because alpha and beta are exponents. So do you remember the exponential representation? What does this angle symbol does? What does it do? It's just e to the power of j theta 1. So it's actually an exponent, right? So that's why you multiply the magnitude of z1 and z2 and then just add the angles. Okay? So see, multiplication, it's much easier in polar form. You don't have to do it, but if you understand it, it's going to help you a lot. So can you guess what it's like to divide two complex numbers in polar form? Divide the coefficients, subtract the angles. Okay? I think I have an example here. Yeah. So what is z1 times z2 here? z1 times z2 is equal to 5 times 10 okay? How do you divide? Good. Important result of this, especially for the last 2-3 lectures. First of all, look at the left side. Z is equal to magnitude with theta. Z conjugate is magnitude with negative theta, right? What happens if I multiply Z and Z conjugate? So the magnitude squared, and I should add the angles. Angle would be 0. Do I need to write the angle of 0 or no? Why not? Why is it 1? E to the power of j0 is 1. E to the power of 0 is 1. That's why I don't write it. So any product of any number with its complex conjugate, it's equal to magnitude squared. Okay? Any problem, any questions about sinusoidal, about complex analysis? No? Okay, let's move to sinusoidal signals. Now, first of all, when I'm talking about sinusoidal signals, I don't necessarily mean the sine function. It could be cosine function. You'll see later that the only difference between them is something that sometimes is not distinguishable. For example, on the scope screen. If a signal is shown to you on the oscilloscope screen, you can't say it is sine or cosine. It can be both. It is both, actually, because the only difference is something called phase that we will talk about later. Now, for the generic form of any sinusoidal function is in this shape. Vt as a function of time, because the horizontal axis is time. Vm sine omega t plus phi plus vdc, or in cosine form. Doesn't matter which one you write. After the next lecture, we are going to define some convention of working with cosine most of the time, but right now it doesn't matter. We're going to define different parameters in these two equations. First of all, the parameter that is behind sine and cosine, Vm, is called the amplitude. Okay? It's a measure of how your signal is stretched along the vertical line. But the textbook definition of that is the peak-to-peak value of the signal divided by 2. Now, I didn't define peak-to-peak value for you, but I'm guessing it is very obvious what it means. From the negative peak to the positive peak. I defined it as peak-to-peak, and then half of that is called amplitude of any sinusoidal signal. Okay? So it's a measure of how stretched the signal is along the vertical axis. Now, so if you look at the black line, the horizontal black line, if I measure from the black line to the positive peak, it's also equal to amplitude. So can I give that as a definition of amplitude as well, or no? Can I define amplitude as the distance between 0, the horizontal line, to the positive peak, or from 0 to the negative peak? Why not?
You could have a vertical shift.
Yes, that's the problem. In this specific case, this signal is centered around the horizontal line. But if it is shifted up or down, then your amplitude is not from 0 to positive or negative peak. Okay? Did that make sense? So generally, your signal can have some shift up or shift down. Can you tell me which parameter in the equation or in the expression of the function is representing that shift? VDC. And is the name intuitive enough? VDC, is the label good enough? If yes, tell me why. Is it time dependent? No. That's why we call it VDC. The rest of the function is time dependent. It's cosine of omega t or sine of omega t. Okay? That's why we call this constant value DC value. Okay? It's a shift along the vertical line. So we talked about Vm, which is amplitude. We talked about VDC, which is the shift along the horizontal line, along the vertical line. We have two more things to talk about, omega and phi. First of all, very important. Don't call that W. That's not W, that's omega. That's a Greek letter, okay? And phi or phi, both are fine. Should I also define t or no? T is time. It's a variable. You're not supposed to have a value for that. If you have, then this is not a function anymore. It's just 1 point. Okay? So t is a variable. Put that aside. I need to talk about two constants that I have here, omega and phi. First, omega. Let's forget that we are talking about sinusoidal function or whatever. Can someone define frequency for me? Imagine that I'm just someone from outside the university. I'm not from electrical engineering background or whatever. Just define frequency for me.
It's how often something happens.
Perfect. Based on your definition, how often something happens? Can you tell me the units of frequency?
Something over time.
1 over time. If someone has a problem with understanding why how often is defined as 1/2, let me give you another example. Imagine that we have two buses, two campus buses at Louisiana. I wish we had. Like they go around campus and come back to the original. The first one takes 5 minutes to go around the campus and come back. The second one takes 10 minutes. Okay, there are different buses, different routes, but one of them takes 5 minutes to come back and the other one takes 10 minutes. In an hour time, in a period, in an interval of 1 hour, 60 minutes, how many times the first bus, the 5 minutes bus, can complete one cycle of going around the campus? 12 times. The 5 minutes one. 12 times, right? How about the second bus? 6 times. So let me ask you a very common question. Which one is more frequent? The first one, okay? But if you look at the number that I associated with them, 5 minutes and 10 minutes. 5 is smaller than 10, right? But it is more frequent. So does that kind of justify why I consider 1/time as the frequency? Because that's exactly the behavior is opposite. So you say the first one is more frequent. So that's why I define frequency as 1/time. Okay? Now, what do I call the inverse of frequency? Period or cycle. What does it mean? It means that the first bus, how long does it take to complete one complete cycle? 5 minutes. That's why we call this a period or a cycle of the first bus. What's the cycle or period of the second bus? 10 minutes, okay? And see that how they are defined is F is equal to 1/capital T, which is defined as the period, okay? So let me talk about this here. F is equal to 1/T. The textbook definition of frequency is the number of complete cycles in 1 second. Okay. Now that you hopefully know the definition of frequency, let's define angular frequency. What does it mean? What's the difference between frequency and angular frequency?
The frequency of a change.
Sorry again?
Just be how frequent angle changes or something?
Sort of, yeah. For any circular movement, you usually assign angular frequency, okay? For example, if you are considering something that changes angle and return to the original point, okay? What is changing is actually the angle. That's why we call it the angular frequency. And it comes back to the original point, okay? And since sine and cosine are periodic function, right? So whatever is inside the parentheses of sine and cosine is going to change between 0 and 2 pi. And after 2 pi, the behavior is the same as, for example, 370 has the same behavior as 10 inside the parentheses. That's why we call it angular frequency. What is the unit? The unit literally is just the same as frequency 1/second. But in order to distinguish them, we just add radian per second, just to mention that it is about angles, okay? But you can easily add them together, meaning that radian is not a real unit. Radian per second is the same as 1 per second, okay? So they are not different, but we only add radian to be able to say These are different entities. Okay, so I talked about frequency, angular frequency, which is 2 pi times f, whatever frequency that you have. If you multiply it by 2 pi, it will give you angular frequency. F is 1 over t, so omega is 2 pi over t. What is the famous units that you know for frequency? Hertz, right? And yeah, so hertz is the other term for 1 per second or second inverse, and that's it. Okay, now here, can you tell me which of these lines, horizontal lines, are representing the period of this wave or function? This one, is this equal to period? Why?
Beginning all the way in, all the way through one full cycle.
Yes, it completes one full cycle of the function. So it moves from the positive peak to the next positive peak. That's why it's called one period. What else is one period? The one to the right. It goes from 0 to 0. Am I correct? Why not?
It goes from 0, but that descending slope to the same.
So it goes from 0 and decreasing to 0 and decreasing. That's why it's called one period. For example, if I only consider the first part of the definition from 0 to 0, I should be able to call this one also a period, while I know it's not, because it goes from 0 increasing to 0 decreasing. These are not the same points. It hasn't completed one full cycle. So what is it? The left bottom. T over 2. The purple one also T over 2. How about the other, the one that is left? T over 4. This distance is T over 4. From the positive peak to when it goes to 0. Okay? Any problem with understanding frequency and period? No? Okay. I want you to compare these two signals. What is the same between signal 1 and 2? Same amplitude. What is different?
Their frequency,
Which one is higher?
the red one.
How about period? Which one is higher? So, is there any problem? See, the red one is just faster changing with respect to time. That's why it has a higher frequency. What can you say about F1 and F2? Sorry?
F1's amplitude higher than F2.
No. F is the frequency. It's not a function. What can you say about F1 and F2?
They're the same.
They are the same. Why?
They're the same period.
Because they go to 0 together, to peak together, and to 0 and decreasing together. What is different between them? Okay. I mean, it's not maybe that obvious, but what is the same between these two signals?
The frequency and the amplitude.
Same amplitude, same frequency. What is different? Different phase, meaning that they're not going to peak and zero together at the same time, while their frequency is exactly the same.
Because their omega is the same.
Yes, the omegas is the same, okay? But the phi is not, okay? We're going to talk about that. Any problem? So what is the definition of phase? If you look at where you first saw phase, it was in this expression. Okay? So let me actually write something here, something that you've seen before. If you have the plot of ft, are you able to plot ft plus 2? Do you remember how you did that? You moved it to the left by 2 units. What if it was t minus 2? You moved it to the right by 2 units. Okay, it was the opposite. Okay, so positive 2 moved it to the left, negative 2 moved it to the right. Okay? Now, based on that, you can understand that phi is actually a measure of how shifted your signal is along the horizontal axis. It indicates how much the signal is horizontally shifted along the time axis. Also, I've written to describe the signal's starting angle at t equals 0. Why? Because if you look at the total angle, by total angle I mean whatever is inside the parentheses of sine, and set time to 0, what is left? Phi or phi, okay? So that's the starting angle at t equals 0. Now, because this is color coded, and of course the units of phi or phi is radians or degrees, because that's angle, right? Because it's inside the parentheses of sine, it should be angle. Now, because this is color coded, it's easy to say which one is which. But the black signal compared with the function v1, if it wasn't black, color coded, how would you tell that the black signal is associated with v1? At 0, if you plug in 0 to v1, what's going to happen? It will be sine of 0, which is 0. So 0 and 0 should be a point on the function. The only function that has the intercept 0 and 0 is the black function. Do you agree with that? So that is one. Now, how would you tell the red one is v2?
That would be sine 0 would be sine of t0 is the square root of 2.
Plug in 0, it's sine of 60 degrees, and it's equal to root 3 over 2 is a positive number, so as 0 should be positive, the red one. How about the blue one? At t equals 0, it's sine of negative 60, it's negative root 3 over 2, it's a negative value, so it's a blue function. And I want you to see something else. So when your phase is positive, what's going to happen to the original signal?
It shifts left.
Positive phase. Left shift. And negative phase, right shift. Okay? Let me add a little complexity to this problem. So here is my reference point that I was considering. So this was the reference point of my original signal. Then I talked about shifting it to the left and shifting it to the right, like this. And I talked about positive and negative phase. What if, instead of considering the top of that dune, whatever that is, that peak, I consider this one? Is it shifted to the right or left compared to the black
Which one?
peak?
Red or blue?
Huh?
Red or blue?
I'm talking about the blue. It's shifted to the left. The peak of the black should be shifted to the left to give you that peak of the blue one. So which one is it? Should I shift to right or left? What does it mean? Both will give you the same?
What did you ask?
This is what I'm asking. I want to change the black signal to get to the blue signal. Should I shift right or should I shift left?
Shift right.
So if I shift left, what's going to happen?
You could do that.
They are exactly the same thing. So, in order to make sure that you're following what I'm saying, is there any other way that I can write V3? These two are exactly the same signals. Now, let's see if it is consistent with our understanding of shift left and shift right. So the first one is negative phase. It should be shifted to the right. The second one is positive phase. It should be shifted to the left. And they are exactly the same. They are not distinguishable from each other. Okay? So I want you to understand, because of the way sine and cosine behave, because they are periodic, it doesn't matter which one you consider. Which one we usually prefer? We prefer to work with smaller numbers. Okay? Example. A sine wave is 0 and increasing at t equals 10 millisecond, and the succeeding positive maximum of 10.6 occurs at t equals 18.2 millisecond. Let's plot whatever information that we have. So, these are the information I have. It's 0 and increasing at 10 millisecond. This is 10. So this is t in millisecond. And this is your f of t. So what is the behavior of the function at 10 millisecond? 0 and increasing, right? It's not the full sine function, it's just that piece around 10 millisecond. Well, how about the rest of it? It's probably something like that, right? The only part that I'm interested so far is that it's 0 and increasing around 10 millisecond. What is the next piece of information? Here is 18.2 millisecond, which is the positive maximum. Can you tell me what is this value? 10.6. It's given to you. The maximum of 10.6 happen or occurs at t equals 18.2 milliseconds. Okay, it's asking you to express the function c1 in the form of c1 sine of omega t plus phi, where phi is the smallest positive value. Just to don't kill your hopes, this is a difficult question. Okay, it's a web work question, so if you go to web work, you will probably see this or a very similar one, of course, with different numbers. So this is not very easy. Okay, so I have, this is my function. Which parameters I need to determine? C1, omega, and phi. Which one do you know instantly? What is C1? Why? How do you know 10.6 is the amplitude? It says the maximum is 10.6. Does it mean that 10.6 is the amplitude? Under one condition, it is amplitude. What is that condition? VDC is 0. Is VDC 0? Yes, because in the form that is asking you, there is no VDC value. There is no constant value. So we can be sure that 10.6 is actually the amplitude. Okay, what is the next parameter that we need to find? Omega. So is there any information on the plot that gives us any hint on omega? So can you tell me what is this interval? T over 4. So T over 4 is equal to 18.2 minus 10, which is 8.2 millisecond. And from here, I can find T, which is 32.8 millisecond. Okay? From T, I can find, or, what did you say before?
Omega.
Yes, thank you. 2 pi over T, and that is the value I have, 191.56053. The reason I included so many digits is because web work is stupid, and last quarter we had a lot of issues not entering all the digits and it gave us the wrong answer. Okay, so that is your omega. So what is the function that I have so far? C1, oh no, sorry. 10.6 sine 191.56053 t plus phi. That is my function. There's one more thing left to calculate, and that is phi or phi. What should I do?
Plug in 10 milliseconds for W. So,
Which one is easier to plug in? 10 or 18.2?
10.
10, why?
Well, sine is 0.
Because the sign becomes 0, okay? It's easier to work with the 0 on the other side. So at t equals 10 millisecond,
Would that be treated as 0.01 seconds?
sorry?
Would that be treated as 0.01 seconds or keep it as?
Yes, yes, you should plug it in as second. Why? Why? Because your omega is in what units? Radian per second. It should be multiplied by second to give you radian, right? So if I plug the value 10.6 sine of 191.56, no, yes, 56053 times 0.010, which is 10 millisecond plus phi, that should be equal to 0, right? Now, a reminder. If sine of x is equal to 0, what is x?
Oh, zero.
Only
Or negative 5.
negative 2 pi, negative pi, 0, pi, 2 pi, so on and so forth. Generally, you write it as k pi, which is any multiple of pi. Okay? It has infinite answers, this equation. But if you look at here, it says where phi is the smallest positive value. So this is what I'm going to do. So far, what I know is that inside the parentheses, this guy, this is my x, right? And this should be either negative 2 pi, negative pi, 0, pi, 2 pi, and so on. So let's multiply it. Is it 1.9? Yes. So based on here, I can say that 1.91561 plus phi, that should be equal to. What are my options? Let's start with negative 2 pi, negative pi, 0, pi, 2 pi, and see if I can get anywhere from them, okay? Let's start with negative 2 pi. Remember, negative 2 pi almost is 6 something, negative 6 something, right? So if that is negative 6 something, and then this goes to the other side, is phi positive? No. So the first one is not acceptable. Right? Do you see what I did? So just solve this equation. 1.9 plus phi equals to negative 2 pi. Does that give you a positive phi? No. So that is not acceptable. Negative phi. The same goes for negative pi, right? How about 0? Also negative. So it makes sense to just ignore all the negative angles. Let's go to pi. It's positive because pi is 3.1415. Okay? So it's greater than 1.9, and it will give you a positive value. But it's not going to be my answer. What's wrong with that?
Oh, your period would be starting at the negative side. Right. Where sine will start going negative first, right? Instead of positive.
Yes. So the usual sine function that you have, this is the generic one, okay? If that is x and that is sine of x. Can you tell me what point is this, the middle one?
That's pi.
That's pi. That's 0. And that is 2 pi, right? So if you look at the statement of the problem, what is it saying? 0 and increasing. At pi, is the function 0 and increasing? No. That's why you should ignore pi, 3 pi, 5 pi. Remember, these are not x. These means wrong, incorrect. So x is equal to, or I can write it as 1.91561 plus phi is equal to 2 pi, which gives you the phi of 4.36758 radians, and you can change it to degrees. I have 250.24390 degrees. And what is your final function? F of t is equal to 10.6 sine omega, which is 191.56053 t plus 250.24390 degrees. What kind of... Okay, these are some trig identities. You don't have to memorize them. Whatever you need is going to be given to you in your third exam. You know that you have a formula sheet for the third exam. So I'm going to talk more about why we don't actually need trig identities in this course. We're going to do something alternative. Any question?